Alright, let's continue with the design of composite section. So let's understand the process of designing a composite section. So, what is it we are going to do in composite section design is typically it involves determining the required dimensions. Either, for example, you can use a standard precast pre-stressed beams to support the design loads, or you want to find the section modulus of the precast sections, provided you are given the depth of the cast in place slab. So either you can use standard precast sections which are typically rated for certain loads, or your deck slab thickness is fixed and you want to find out what are the section modulus of the precast pre-stressed beam is required. So these are the two things that typically is the typical scenario. So the design, as explained in the previous slides, it involves analyzing for various load stages. And what are the key considerations that we need to include? We need to understand the relationship between section modulus, the load in different stages, the limits on concrete stress, and what is the pre-stressing loss ratio, right? So we need to, we have studied this Magnell's graphical method, right? So you have to satisfy 4 stress limits. Similarly, here also we need to make sure that the stress limits are within the acceptable values. And stress conditions, as we explained, we need to do the analysis for different stages of construction. You can see in composite construction we have studied at the time of transfer of pre-stress what are the stresses, and then when the dead load of the cast in place slab is placed, depending upon whether it is propped or unpropped, how do you do the analysis. Then for the live load moment. So for the live load moment, it doesn't matter whether it is propped or unpropped. The entire composite section, we have seen that it will be resisting the applied moment. And then the load distribution between the precast and cast in situ components. We have also done the stress analysis in the previous part. Now, these are the various load stages. Again, just a quick recap. If you take this as a precast element, right? So this will be subjected to initial pre-stress. Let's say you will have 2 components, concentric stress component and the pre-stressing moment component, depending upon whether you are doing the calculation at the top fiber or bottom fiber. Accordingly, use your section modulus. Now this is after loss. Typically, eta factor, we take it to be 0.85. Assuming that 15% pre-stress will be loss, right? So we do the calculation, same, we reduce the by eta factor. Then the dead load, again the dead load will be resisted only by the precast segment. If it is unpropped, then the live load moment that will be resisted. These are the different stages. Now let's look at it. What are the critical stress conditions that will control the design? Typically, the critical stress condition will be at the bottom edge of the precast member. This is for both the minimum. When the minimum moment will come? When it is only when you are doing a transfer. So that is where this minimum load will be typically moment that will be coming from the dead load of girder. Okay. And maximum will be coming from all the loads, service loads, basically MDL plus M live load. Right? So these are the bending moments that we need to do. Now let's see, how do you calculate the section modulus of the composite section? So again, as I told you, we have to satisfy the stress limits if, let's say, F inferior is the stress due to pre-stress at the bottom of the precast. Now that available compression, if I take compression as positive, tension as negative, for example, this is the pre-stress at bottom, and the self-weight moment, as you know, if you take tension as negative due to the self-weight, it is going to reduce the compression that is induced at the bottom fiber. So that's why we are taking F inferior minus M minimum by ZB, which should be less than or equal to the allowable concrete stress in transfer, because this is the equation that will govern while you transfer the pre-stress, right? Now for the composite section, when you have live load also, now you can see the available pre-stress will be reduced by eta factor, because now the losses have already happened. Eta factor, as you've seen, usually we take it as 0.85, and that is compression positive. Again, the dead load moment will reduce the net compression, then the live load moment will further reduce the net compression. Now what is ZB and ZB bar? Whenever the dash is included, that is the section modulus for a composite section. As we've seen, dead load is resisted only by the precast, but the live load will be resisted by the composite section. Now, because of this, at the bottom, when both live load and dead load are acting, this can become negative, right? So this stress, if you put as negative, this is the allowable tensile stress in working conditions. W stands for working condition or service condition. Working condition or service, right? Service condition. So then you find the equation 2. Now somehow I have to juggle this equation 1 and 2 by eliminating this pre-stress component that is at the bottom, F inferior, look the stress from pre-stress at bottom, including both axial and pre-stressing moment component. As we said, FSCP or the pre-stress at the bottom and top of the precast beam. Then if you eliminate this by solving, then we can find expression for your section modulus for a composite section in this form. Okay, so this equation will be very useful if you know your stress limits, and if you can estimate your live load and dead load moment, then you can put your allowable stress limits and then directly find out what should be the section modulus for a composite section. Then accordingly you can decide what should be the thickness of your precast slab. Now in addition to that, the amount of pre-stress required at the bottom also can be decided to ensure that the F inferior, which is again that is the amount of pre-stress at the bottom, we need to have adequate compression so that for a type 1 member this will never get into tension, right? So this also we can find out using these equations. So you can see MDL by eta ZB plus MLL by eta Z prime B, which is a composite section modulus, and FTW is the allowable tensile stress under working conditions. So everything you can find out an expression from this equation 2. Directly you can find an expression for F inferior in this form. So equation 2 can be modified to in this form, right? Now again at the same time, the stress at the bottom also cannot get into tension while you are transferring the pre-stress. So this is again, that's why the stress, because the tension is taken as negative, that is the reason the equality sign here is greater than or equal to, right? So compression, when it is negative, we want to make sure that the stresses are within the acceptable limit by enforcing this inequality, this kind of inequality. And FTT is the stress at the top fiber during transfer minus M minimum by ZT, which will be the stress that will be coming from self-weight, and that will induce some compressive stresses. So this net, we have to make sure that it is F sub, or the stress at the top of the precast beam is greater than or equal to these values, right? Now what are the section modulus for the precast pre-stress beam for a given slab depth? So this is what we have seen. We are finding out the section modulus of the precast element, right? Now what is the section modulus once your slab depth is fixed? Okay, if slab depth is fixed, ZB, you can see this is only for precast, not for the composite section, right? So this again can be derived in a very simple form, in the form of the dead load moment and the minimum moment that is coming from precast beam dead load, and considering the allowable stresses in concrete at transfer and working, then you can derive this expression for your ZB, right? Now the required pre-stress, again, which are calculated from equation 4 and 5, again they will be checked under working loads. Okay, So let's, these are the stress equality, we have to satisfy the stress limits. Now let's go through an example problem that will clearly explain how this entire process is being done. Now we want to design a simply supported precast pre-stress composite slab, and the data are given below. Width of the slab is half a meter, depth of the slab is 100 millimeter, effective span is 5 meters, and depth of the precast beam is 300 millimeter, and width of the precast beam is again 100 millimeter. Grade of precast slab is M60. Grade of topping slab, as I said, typically the grade slab or the cast in place slab will be having lower grade. The pre-tension tendons are located at mid depth of the precast slab, and during the casting of the slab, the beam is not really propped. Okay, this is actually beam. Okay, the slab has to carry the live load of 10 kilonewton per meter square, including the finishing loads. Okay, now let's go through the process. Load calculations are very simple, straightforward. You know the depth of the slab, width of the slab multiplied by unit weight will give me 1.25 kilonewton per meter. Now the beam dimensions are 300 by 100. Again, that is multiplied by 25 to give 0.75 kilonewton per unit load. And the live load is 10 into 0.5, which is acting over the entire width of the slab. So that is working out to be 5 kilonewton per meter. Then moment calculations are WL square by 8 because they are simply supported. So 1.25 into 5 square by 8 will give me 3.9, and the beam moment is 2.34, and the live load moment is 15.62 kilonewton meter. Now section properties are this for precast beam, right? We have 100 by 300. So the A1 is 30,000 millimeter square, and Y1 is 150 millimeter. Again, it's a rectangular cross section. So the maximum depth of the fiber from the neutral axis is 150 to the top and bottom fiber. Moment of inertia is 2.25 to 10 to the power of 8. Z1 or the section modulus is 1.5 to 10 to the power of 6. Cast in place properties are this, and now we want to, because they are having different concrete strength, now we have to employ modular ratio. As you know, E is always some constant square root of FCK. So compressive strength. So we divide the square root of concrete strength to get your modular ratio. So we get this as 0.64. That means the slab is having, if I want to convert the slab into an equivalent precast beam grade, I need to multiply with modular ratio 0.64 for stress calculation. So let's see how do we do that. Now you can see this is the section and your pre-stressing is at 150 millimeter. Now let's calculate the composite section property. Again, simple calculation. This is area of the precast element plus modular ratio times the area of the slab, and then centroid using your regular process. This plus the area times y should be equal to this composite area. Then you get your YBC as 146.34 and 253.65. The distance of the top and bottom fiber from the CGC and is about, CGC itself is about 253.65. So the distances of the bottommost fiber is 253.65. Top fiber is at a distance of 146.34. Now the joint is at a distance of 46.34 from here, like this, from the CGC. And now the amount of inertia for a composite section, again we can calculate. Now the slab is getting reduced by modular ratio 0.64 into 500 into 100 cube by 12, and this is using parallel axis theorem, and this area plus distance square will give me the moment of inertia of only the slab. In addition to that, I should also take moment of inertia of these two are slab and these two are for the precast beam. So when you add them up, you get your total moment of inertia as 8.74 into 10 to the power of 8. Right. So once you do that, the section modulus at different locations. For the bottom fiber, it is 3.44. For the top fiber, it is 5.97. And the section modulus at the junction of the slab and the beam is 1.89 into 10 to the power of 7, because the Y here is 46.34, lower value. Right. So now let's look at what are the pre-stress requirement. We need to avoid the tensile stress at the bottom during service condition, and the section is unpropped and the pre-stressing is at the center. So we can write the equation. The stress at the bottom has to be, no tension should come, so we can equate that to 0 tension. So this is a concentric component, PE by A1. Now the slab and the beam, both of them will act as a dead load. That divided by Z1 will give me the stress at the bottom. And the live load will be acting resisted as a composite section. So if you put all of them, and if you can find out, because if you equate it, you can find out the expression for effective pre-stress. So once you substitute all the numbers, then we get the effective pre-stress requirement as, right. So you can substitute, we have calculated already slab moment, beam moment, section modulus Z1 we have already calculated. Section modulus for the composite section we already calculated as 3.4 into 10 to the power of 6. You plug in all the numbers, then you find an expression for your effective pre-stress force as 261 kilonewton. Now 261, I just increase it by 20% because I need to, because I am calculating the initial pre-stress, right? Because losses here, just to be on the conservative side, typically it is 15%. But I am slightly overestimating by multiplying by 1.2. So I get initial pre-stressing force as 313 kilonewton. Now if you assume 7 mm wires are used and with an ultimate strength of 1600 megapascal, the force per cable, I can usually for wires you can stretch up to 80%. So 0.8 times FPU times your area of your wire, right? And this is your FPU. This is our 0.80%. So when you do that, for each wire, I can put a force of 49.25 kilonewton. Now, for 313, if you divide by 49.25, I need about 6.3 numbers of wires. So we round it off. So we can say that we can provide 7 numbers of 7 mm diameter wires. So what is the force that we put? 7 into 49.25, which works out to be 345 kilonewton. So this is the P0 or the initial pre-stress that we need to apply, then only for the assumed dimensions. Now the stress at the bottom will not get into tension, right? So then the P effective is 0.8, so you get 1275 kilonewton, which is in fact higher than what we have assumed, 261 kilonewton, right? So this is okay. Now we need to check for the stresses in the concrete as well. So how do we do? A transfer, the compressive strength at 7 days, let's say that we are transferring at 7 days. So 0.7 into FCK is 42 megapascal and the allowable compressive stress is 0.44 times FCI, that works out to be 18.5 megapascal. So stress at the midspan when we calculate P0 by A1 while you transfer, right? So this is only at the transfer. So basically you can see that is P0 by A1 because here you don't have MP component. Why? Pre-stressing moment will be 0 because the eccentricity is 0 with respect to precast element, right? So that's the reason only you have concentric component P0 by A1 plus or minus depending upon whether you are calculating at the top or bottom, either it will be minus or plus, right? Because at the top it is going to be negative and the bottom it is going to be positive. So again it depends upon, here compression I have taken it as negative. So while you transfer, bottom will have compression, so bottom will have negative component, the top will have positive component. So when you do that, you get the stress of negative 13 megapascal at bottom and this is at top, right? So we can go up to 18.5 megapascal, but our limit is only 13. So FT, the stress at the bottom is less than FCC allowable. So whatever the amount of pre-stressing section dimension that you have chosen is good for transfer condition. Now we can also, after casting the slab, again still the allowable limit, while you cast the slab, again by the time the precast element would have gained its strength, it would have reached its 28-day compressive strength. So that's the reason FCK, we don't take 0.7 FCK, we take the full FCK, we substitute that the limit is 26.4 megapascal in compression. Now, by including the weight of the slab, you will find that this is going to be this minus or plus. So, this is at top, sorry, this is at bottom and this is at top. So, again, at both the cases, minus 15.65 is or less than 26.4. So, or I should say 15.65 is less than 26.4. So, compressive stress limits at the bottom are again satisfied. Okay. So, this is we have done checking only for the transfer condition. Now, how about the service condition? So, again here you can just, we are noting down for type 1 section, no tension stresses are permitted. At transfer condition, before and after casting the slab, the entire section is in compression. So, there is no tension, even the allowable compressive stresses are well within the, or the compressive stresses are well within the allowable limit. Okay, now we can do the calculations for service. Now, the moment you go to service, my allowable compressive stress will slightly reduce. Instead of going for 0.44, we take 0.35. So, that becomes 21 megapascal. So, now at the joint location, we have seen that at the joint locations where you will have higher compressive stress. So, if you substitute PE by A1, similarly the slab plus B moment divided by Z1, live load divided by section modulus of composite section. You substitute all those things at the joint location. Now, I am getting a stress of 14.18 megapascal. Again, this is less than 21 megapascal in compression. Okay, 14 is less than 21. So, it is okay, right. So, now how about the stress at the bottom fiber? PE by A1, this remains same. Precast system, so this remains same. Only the live load again, which is going to be different. So, the live load moment we have already calculated to be 15.26 into 10 to the power of 6. So, if you, this is at the bottom of the slab. So, when you do that, you get your 0.49 megapascal. Now, for the slab portion, this is for the precast portion at the midspan. Now, for the slab portion at midspan, the allowable compression is 0.35 times FCK. Now, the FCK for the slab is basically 25. So, 8.75 is the limit. So, now let us look at it. These are the stresses that is at the bottom. This is at the bottom of precast. Okay, and this is at joint between slab and precast, right. Now, this is, we are looking at the slab portion, right. Slab portion, when you look at the joint, again this will become MLL by G, so section modulus. This value now will become 1.89 and the stress is -0.82 megapascal, right. Now, how about the stress at the top of the slab? Again, effective pre-stress by A1 minus MLL by 0. Here there is no pre-stress component, it will be 0. It's only the live load component that will come. So, that works out to be negative 2.61 megapascal, right. Because the slab will not having the PE component in both the cases, right. So, that is the reason PE by A1 will become 0. It's only the live load that is being resisted by that slab at the top and the joint location. So, this is how we calculate the stresses. Now, we can plot everything now. Now, again, all the stresses are in compression which are below the allowable limit. Now, we can plot it for an unpropped case. While you transfer -10, -13, everything is in compression. After the slab is cast, again, the slab acts as a dead load. So, it at the bottom, it is going to create tension. So, that is the reason the compression 10 has become -7. Compression stress is reduced. At the top, I add more compression, so that has become -15. Now, at service, if you look at it, we get because of this, now this is for the slab casting, and then this is for the service load where we are going to put some finishing load, and then you have stresses that are coming -2.1 and -0.82, -0.5 and -14. There is a discontinuity because of the live load. This is only due to live load. This is only due to live load, right? So if you substitute that, you get your stresses. This is your net stress, service stress that you are getting, and all of them, everything is in compression, which are less than your allowable stress limits. Now we should also check for the shear. Now shear, we have already spent quite a bit of time on how to calculate, the two shear capacities. One is the web shear capacity and is the flexure shear capacity. Now for web shear capacity, this is the equation. We have explained how we derive this equation using Mohr circle as well. So you can go back to the previous modules on the derivation of this. So FCP is the pre-stress that we put, FCR is the modulus of rupture, and VP is the vertical component of the pre-stressing cable. So you substitute, FCR is 0.24 into square root of FCK, which is 1.89, and FCP is 276,000 divided by 30,000, which is 9.19 megapascal. So you substitute all of them, you get your diagonal web shear capacity as 83.19 kilonewton. Now, ultimate demand, we have already calculated 5 kilonewton per meter, 1.25 kilonewton per meter, 0.75 kilonewton per meter. This is span L by 2, that comes to be 26.5. Now you can see that VC naught is much higher than that of your demand, so there is no problem for shear, right? So, but still we can provide a nominal stirrup, which is at 8 mm diameter stirrup at 300 mm center to center. So when you look at the precast beam, so this is the stirrup, 8 mm two-legged stirrup at 300 center to center, right? And this is how we look at it. Pre-stressing is 7 numbers of 7 mm diameter strand, and the stirrup is 8 mm diameter at 300 center to center. And then you put some nominal bars for holding the stirrups while you are casting the precast beam. And you see here, this upper portion is typically left open, and then it will also act as a shear key for horizontal shear stress requirement as well, right? So though we have not checked explicitly for this example, in fact, this will help you in giving you the shear resistance that we have seen through shear friction theory, how we can calculate that, right? So this is the way that you check for the design of a composite section. Now let's summarize the discussion that we have had on this composite section chapter. We discussed the types and applications of composite construction. We demonstrated the stress analysis for propped and unpropped systems with some examples. We have also explained the deflection behavior for both conditions with some calculations. And we highlighted what is the significance of differential shrinkage. We have seen that because of shrinkage, the slab will undergo tension. For that, we need to actually design for it. And we also illustrated how to calculate the horizontal shear stress, and then how to design the stirrups to ensure that there is not going to be any horizontal slip between the slab and the precast beam. And we also completed one design of a composite section with a simple example. So with this, we are completing this module. Next video, we will be moving on to the next module. Thank you.